अच्छा चले ठीक है let's just one more minute. So ठीक है let's start. I think we were doing it from the other side. We're going to try, and we did we didn't do this question. ठीक है, we did the other one. Question number 7 पे आ जाते हैं. I think we had started this one. Not really sure. कि we did. We did the methanoic acid part comparison. So we had done. This was probably the last thing that we had done. We were talking about the comparison of. Sarah, can you hear me?
Yes, sir.
So we had started talking about the comparison of propanoic acid, propanol, and phenol, and starting with the most acidic uh, to the least acidic. So, also you had to explain everything about. So we did this thing. Okay, this was the last one. Then is seeing that methanoic acid and propanoic acid they have similar strengths. Describe a chemical test to distinguish between the two acids. So you're supposed to distinguish between the two acids. Now, one way to distinguish between the two acids is that remember there's just a couple of carboxylic acids that do get oxidized. They can be oxidized. Methanoic acid can be oxidized to carbon dioxide and water molecules if you reflux it with KMNO4 acidified. So there's going to be oxidation taking place, and the color would change from purple to it's going to change from purple to colorless. So methanoic acid, and there's another acid which gets oxidized, and that's ethane dioic acid. It has carboxylic acid groups on both sides. That also undergoes oxidation. So both these acids they undergo oxidation. So that's one way to distinguish between the two. As a next one, propanoic acid is not going to get oxidized. Next is the ester. That's phenyl propanoate, and it says can be made. So it says it can be made from phenol and propanoic acid in a two-step synthesis. The first step produces an acyl chloride. For this two-step synthesis, draw the structure of the product of the first step. State the reagents and conditions needed to. So we have a phenol getting involved. Now, a phenol is a benzene with an OH group, and O has these lone pairs. So that's phenol. And remember, when you make an ester with a phenol, he's saying can be made from phenol and propanoic acid. So there's the other ester that you have. Sorry, the other reagent is a propanoic acid molecule. Now remember one thing: propanoic acid is CH3, CH2, and it's C double bond O and OH. Now remember one thing that phenols they are like alcohols, but they don't form esters with carboxylic acids. The reason being that carbon over here is positively charged, and you have these lone pairs over here on this oxygen atom, which are negatively charged, and they attract each other. But the problem with phenol is that the lone pairs are not really there. The lone pairs they kind of overlap with benzene's pi electron cloud. So the lone pairs over here, they're not available, or their charge density is lesser because they are overlapping with benzene's pi electron cloud, which is why, due to non-availability, there's no attraction or there's little attraction. Uh, so to increase the attraction, what you do is instead of the OH, you actually take an acyl chloride. What you do is you don't take a carboxylic acid. You first turn the carboxylic acid into an acyl chloride. You do that by heating it with PCl3 plus heat. Now, when it's an acyl chloride, the positive charge on the carbon becomes greater now. So this positive charge over here it becomes large. And when it becomes large, it becomes bigger. It's now able to pull those electrons, lone pairs, towards itself. Why is it large? Because now it's attached to two electronegative elements. So the positive charge is now a lot stronger, and the attraction to this oxygen would be a lot stronger. And so these two would get together, and the Cl and the H would be knocked out. HCl would be formed as a byproduct. So you can remove the H and Cl, and the oxygen, which has this negative charge because of the lone pairs, would be attracted to the carbon over here, and they would bond with each other to form an ester link. So this is what's going on over here. Now, what does the question exactly state? It states that draw the structure of the product of the first step. So you draw an acyl chloride, state the reagents and condition needed for each step of the synthesis. For this last step, the reagent for esterification, the reagent is NaOH. It's NaOH aqueous. Alkaline conditions are used. For the first step, the reagent is PCl3 plus heat. Just 1 second. Achha, so it's NaOH aqueous. So the reason it's NaOH aqueous is because phenol is a kind of acidic. You want the H to be lost. And under alkaline conditions, the H would be lost very, very easily. So the two-step process of esterification uh, is this. You first turn it into an acyl chloride, not a carboxylic acid. A carboxylic acid is not going to work over here. And the next one is you just reacted with the phenol. TK, is this clear? You clear, Sanuko?
Yes, sir.
And so next is K. It's about compound Z. A propanol is saying an unknown compound Z is propan-1-ol, propanol, and propanoic acid. The proton NMR spectrum is dissolved in CdCl3. From the proton NMR spectrum, identify Z. So what is Z? One thing that you can easily identify, and let me see if I have the data booklet somewhere open. I have the data booklet. One thing, remember, in the NMR spectrum that can be easily identified is this thing. Okay, if we go to the NMR spectrum, it's not needed. It's this one. If I go to the NMR spectrum, you would notice that if you look at carboxylic acids, and if you notice this thing, carboxylic acid OH, the H proton in carboxylic acid, this one, it resonates at a pretty high chemical shift, 9 to 13, which is very far away from all the other ones. So 9 to 13, that's, and if you go back over here, you would notice that there's an absorption that's happening in 9 to 13, and that would pretty much indicate that it's probably a carboxylic acid. I mean, it probably is a carboxylic acid, but there's a chance of a propanol as well. Go back because propanol is also very close to it. An aldehyde, that's this one, that resonates at 9 to 10. So ours is probably further away from that. It's around 12, much higher than that. So the chances of propanol are kind of slim. And propan 1-ol is out of the question because the OH does not resonate at that range. So it's definitely a carboxylic acid. You're left with carboxylic acid. Uh, so propanoic acid, that's the answer. And you can also compare all the other things about this molecule. Okay, if it's a carboxylic or propanoic acid, so if it's propanoic acid, you're going to have three absorption spectrums, uh, three absorption frequencies. This OH would resonate, this CH2 would resonate as well, and there's going to be a CH3 that would be resonating as well. So you have three chemical shifts. And the splitting pattern would be that there's going to be a singlet. The OH peak never splits. So that's going to be a singlet. And the reason it never splits is that the O lone pairs they shield this H proton from interference from all the other protons. This CH2 has three neighboring hydrogens, so it's going to be a quadruplet. And the n plus one rule. This CH3 over here has two neighboring hydrogens, so that's going to be a triplet. So you have a triplet, a quadruplet, and you have a singlet. So that's exactly what you are getting over here. That's just from the NMR spectrum identifies E, so that's propanoic acid. State one feature that would be seen and why uh, in the proton NMR spectrum of each of the two compounds that are not Z. I said so not Z. So he's talking about aldehyde, and he's talking about so so you have an alcohol. An alcohol has this OH. One is propan one also. It has an OH. You can open the data booklet and you can notice that the OH normal alcohol OH, this one over here, it resonates at 0.526. So there is no absorption happening, no singlet at 0.526. And the other one was an aldehyde. So the aldehyde would have an aldehyde peak. It would have a CHO peak somewhere, and that which we just studied earlier. That where's the aldehyde? Aldehyde would resonate at 9.3 to 10.5. So that's also missing. So these were the two unique peaks that you're going to get at these frequencies. So that's pretty much it. I think we did this question earlier. So let's go back and do the previous one. So question number 6. Now, question number 6.
We did discussion.
So we did this question. So let's do the previous one. So let's try and do question number 5 now. Now, in question number 5, the first thing is you have to write the electronic configuration of a copper atom. That's easy. It's going to be 3p6. And remember, it's a special case, so 4s does not get completely filled. Instead, the 3d has 10 electrons. And copper 1 plus would be 3p6. Electrons are always lost from the outermost. So it's going to become 3d10, and 4s would become 0. You don't have to write 4s. That's one thing. And then you have copper plus 1 ion form a linear complex with Cl minus 1 ions, which are monodentate ligands. Uh, Draw the structure of this complex and include its overall charge. So it's a linear complex. So that means if there's a copper 2 plus, sorry, 1 plus, linear means there's going to be a Cl minus 1 with its lone pairs, and they would be natively bonding to it. And there's going to be another Cl minus 1. And so that's a linear molecule. And the overall charge on this complex is going to be minus 1 if there are two Cl minus 1s. If there are two Cl minus 1s that are involved in this. As the next one is that copper 2 plus ions exist as an octahedral complex UH2O6. Complete the three-dimensional structure diagram of the shape of this complex, name its shape, and label and state the value of one bond angle. So this is going to be uh, an octahedral arrangement where you would have water molecules at the top, with the lone pairs water molecules at the bottom. There are going to be water molecules on each axis. And the overall charge on this is 2 plus. Okay, this is an octahedral shape, and all the angles are 90 degrees. Let's have the next one. Okay, when NH3 is added to copper 2 plus dropwise at first, and then in excess, two chemical reactions are shown. So what happens? Reaction number one. What's going to happen when you add NH3? The first thing that's going to happen is that when you add a few drops of NH3, the NH3 acts as a base, and when it acts as a base, it starts to produce. It reacts with water molecules and ends up producing these NH4 plus one ions. And OH ions are also produced as a result. And initially, right at the beginning, the OH ions are the ones that act as ligands. So what happens is that this CuH2O6, six water molecules attached to it, having a charge of 2 plus, the OH ions come in and they start knocking out the water molecules to form a copper hydroxide precipitate. And your four water molecules, they get knocked out. So that's the first step that's happening, and a pale blue precipitate is formed. Okay, these reactions, they have to be remembered. So you end up forming a pale blue precipitate. और उसके बाद when you add an excess of NH3, that's when further ligand exchange happens. When you add more NH3, then what happens is that this blue precipitate, copper OH2, with four water molecules, if you add further NH3, you keep on adding NH3, then all the ligands, they start getting displaced or substituted or exchanged by NH3. And there could be any amount of NH3s that could be substituted. So you have two OH minus ones getting knocked out, you have two water molecules getting knocked out. This could be any number of NH3s that could be substituted possibly in the reaction. So the equation and the observation would be that this blue precipitate, it's going to be dissolved to give you a deep it's going to dissolve to give you a deep blue solution. So this is what's going on. अच्छा उसके बाद ये कि what's the next question? अच्छा now this one they talk about EDTA as a polydentate ligand. The solution of EDTA is added to a solution containing copper. A new complex is formed. The formula of this complex is Cu EDTA and the charge is 2 minus. Name the type of reaction occurring here. So this is ligand exchange. He's already told you that it's a polydentate ligand. So one ligand, water, is getting displaced by another ligand. So this is ligand exchange. And he's asking for the write an expression for the stability constant of Cu EDTA 2 minus. Now for that, the first thing is you would have to write the equation. You should be You should know what the equilibrium is. So there's 6 water molecules, and you bring in one EDTA 4 minus, I think. And a ligand exchange happens, and you get this thing, Cu EDTA 2 minus. And there's only one of them, EDTA 2 minus. The reason you're getting a 2 minus charge is EDTA is 4 minus and Cu is 2 plus. So overall, you get a 2 minus charge, and the 6 water molecules are getting they're getting displaced. अच्छा, अब उसके बाद ये कि K stability is just the equilibrium constant for this. It's products over reactants. Remember, in an aqueous solution, you don't write water in the expression because water is in excess and its concentration would be a constant. So it's going to be products, which is Cu EDTA 2 minus divided by the reactants, and the reactants are CuH2O6. Its concentration and EDTA 4 minus concentration. So products over reactants. That's your expression. ठीक है, is this clear? Abhiya, Sara, is this clear?
Yes, sir.
So then after that, the medical value of EDTA is this. State what this tells you about the complex ion. That means that if the K stability is really really high, that indicates that it's a very stable complex. Why is it a stable complex? A very high value means that there's more chances of the products forming. The number of products or the concentration of the products is very high. Only then would you get a very very high value. That means the reaction is favoring the forward side, and that means Cu EDTA 2 minus this complex is readily formed, and it's a very very stable complex. Next one is ethane diode. Explain what is meant by the term bidentate ligand. So what's a bidentate ligand? What's a ligand? Ligand is anything that has a lone pair and forms dative bonds with the central metal ions. A bidentate ligand is that can form two dative bonds. So it has two lone pairs and can form two dative bonds with a central metal cation. ठीक है, lots of molecules are bidentate ligands, for example. ठीक है, let's just but we got an example for C2O4 minus 1. This one over here is a bidentate ligand. Why? Because the Fe2 plus is in the middle, and the oxygen lone pairs they're getting surrounded by oxygen lone pairs, and each molecule is bringing in it's forming two dative bonds. So it's a bigger molecule, and lone pairs over here, lone pairs over here. So two dative bonds. So all these are examples of bidentate ligands. As if the next one is when ethane diode ions are added to a solution of zirconium ions, 4 plus a complex ion containing C2O4 and 1 4 C2O4 2 minus and 1 Zn4 plus is formed. All four ethane diode ions act as bidentate ligands. Give the formula of the complex ion. Explain why this complex ion is not octahedral. So remember, each one is forming two dative bonds. And remember, they've said that there are four of them involved. Okay? They've written four over here. So there's one zirconium bonded to four of them. So that's, if there are four of them involved, so that's a total of eight dative bonds. So when you have eight dative bonds, that's not going to be octahedral. The shape octahedral is for six bonds. Okay, so it's clearly not octahedral. That's what you're going to state, that an octahedral shape is formed when you have uh, six bonds or six dative bonds. The one that we drew over here. Okay, we drew one shape over here. This octahedral shape can only be possible if you have six, because each ligand would be on an axis, and they would all be at 90 degrees. So it's only going to be possible if they are six dative bonds. With eight dative bonds, the shape is going to be a lot different, and the angles would be a lot smaller as well. So that's not going to be the correct. So Tika, we're done with this. That's the only thing that, I mean, you just mentioned these two things over here. So are you clear?
Yes, sir.
अच्छा उसके बाद let's do question number 4. Okay, we are at question number 4, and this guy we've seen, what would you see when calcium are heated? So this is about the flame test. You should remember what the flame test is. Uh, Calcium, remember has a scarlet red flame, I think. And the other one, this one, barium has an apple green flame. Okay, so remember the flame test of group 2 metals. Now he's talking about the decomposition temperature of the group 2 carbonates. Why do they vary down the group? And state and explain the variation in the decomposition temperatures. So carbonates become more stable down the group. Carbonates and nitrates become more stable down the group. And decomposition temperature increases because they're more stable. It's harder to decompose. So decomposition temperature is going to increase. Now, that's what's happening. And what's the reason for that? And the reason for that is that at the top, the size of the cation is smaller. So if you have a 2 plus cation, the size of the cation is smaller. And if you have a carbonate ion, because of the higher charge density, what's going to happen is that the cation is going to have very high polarizing power. It's going to attract electrons from the carbonate ion very, very strongly, because it's going to be a small ion with a very strong 2 plus charge. The electrons are going to be very, very strongly attracted. And when they're very strongly attracted, because of that, the molecule is going to get polarized. And when it gets polarized, it's going to break away, and this would form NGO, and this other part would form CO2. Down the group, you have bigger cations, and their polarizing power is lesser. So, one thing that you're going to mention is the first point is going to be uh, the size of the or the ionic radius. It increases down the group. Then you're going to comment on the charge density or the polarizing power. So polarizing power of the cation decreases. Hence, your CO3 minus 2 ion becomes more stable. It becomes more stable when you move down the group. And then it says that magnesium carbonate was heated in an open test tube. So it was difficult to see whether the thermal decomposition reaction uh, took place. So what's happening here? Why is it difficult to see whether a decomposition reaction uh, is taking place? uh, and he's saying it's difficult to see. So basically, you're having problems seeing it, seeing the reaction happen. So why is it difficult to actually see the reaction happening? Because this is the reaction that's going on. Now, why can't you see the reaction happening? The first thing is carbon dioxide is colorless. So if it's being formed, you're not going to see it. It's a 2 mark question, so you're not going to see the carbon dioxide getting formed because you can't see it. It's colorless. The other part is MgCO3. All group 2 compounds are white. So MgCO3 is white, and when it turns into MgO, that's also white. So you won't see any change happening to the white solid. So 2 marks for this because you won't be able to see the thermal decomposition reaction taking place. So, is this question clear? So next is question this one. As a question number 3, saying complete the table, identify the substance liberated at each electrode during the electrolysis with inert electrodes. Uh, and you have to identify the substance that's being liberated over here. Now, you could either use your O levels knowledge because it's a 3 mark question. You don't have to go into a lot of detail, but I'm going to try and do both ways. If you remember your O levels series, at anode you had I minus one, you had Br minus one, you had OH minus one, and you had Cl minus one, and all the rest of the negative anions were higher up. So the ones at the bottom are the ones that got discharged. And at the cathode, you had the reactivity series where you had K, Na, CMG, etc., and so on. And it ended up with platinum at the bottom. So you can either use this one. So silver nitrate, the first one. How many ions do you have at cathode? At cathode, you're going to have silver ions, and you're going to have H plus one. And at anode, you're going to have NO3 minus one, and you're going to have OH minus one. So these two. Who's going to get discharged if you go by O levels? Over here, silver is right at the bottom somewhere. So you're going to select silver. Silver is going to be formed. And on the other side, it's going to be NO3 is somewhere up at the top. OH is at the bottom. So it's going to be OH. And OH turns into oxygen. So you're going to get O2 over here. And you're going to get silver on the other side. So just 1 minute, okay? 1 minute break. So coming back to this question, take this one. That's one way. You figure this out, concentrated NaCl. Just quickly try and do this. How many, what substances do you have at cathode? It's going to be Na plus 1 and H plus 1, right? And if you remember that Na is somewhere right at the top of the reactivity series, so that's not going to be the one that's going to be selected. It's going to be H plus 1, it's going to turn into H2 gas. And the other one over here, if you have Cl minus 1 and you have OH minus 1, and remember O levels, if Cl minus 1 is concentrated, if this one is concentrated, then it's always Cl minus 1 that gets discharged and you get Cl2. So Cl minus 1 would be selected. And for copper sulfate, it's going to be copper 2 plus, and there's going to be H plus 1. And on the other side, you have SO4 2 minus, and you have OH minus 1. And OH is going to be selected. That's going to give you oxygen gas. And on the other side, you will have copper is lower down in the reactivity C, so it's going to be copper. Now, there's one thing that is inherently wrong with this, the way that we did in O levels, and that is you're never going to do this because they weren't asking for the working, which is why it was a lot easier to solve this question using your O levels uh, concept. Uh, but you're not going to solve this question if they had actually asked for working, showing your working as well. What you should have done was that, and I'm going to pick copper sulfate electrolysis. One thing that you should know is, let me do it over here. Now, if you were supposed to show the detailed working, there's going to be one huge difference when you do the electrolysis of copper sulfate aqueous. That's going to be different from what you do in O levels. There's going to be electrolysis. Let me draw the cathode and anode quickly. So here are your cathodes and anodes, and there's this battery. There's copper 2 plus attracted to the cathode. This is the place where it's going to gain electrons. And the other side is, what's the other side? That's SO4 2 minus. And substances would be losing electrons. So here's your cathode, and this is your anode. Now there's one major difference that's going to be different. If you were supposed to show the working of the question, and that major difference is uh, that there is no H plus 1 and OH ions. If it's aqueous, remember water ionizes very, very weakly. Water doesn't really ionize a lot. It doesn't really produce H plus 1 and OH ions. So there are hardly any H plus 1 or OH ions. You're going to assume that there is no H plus 1 and there is no OH ion. There's instead water on both sides. Water is a neutral molecule. It's going to be present at cathode and it's going to be present at anode. And the way you're going to do electrolysis is that at cathode, substances are going to gain electrons. So what you're going to do is you're going to look at the data booklet and you're going to find equations in the forward direction. Because in the forward direction in electrochemistry, substances they gain electrons. Like if I open the data booklet right now and go to the electrochemistry table, okay, so I'm going to mark the equations where I have copper 2 plus. Now I have to look for equations where copper 2 plus is gaining electrons. So I have two equations over here. Okay, if you can see this on the screen, there are two equations where copper 2 plus could be gaining electrons, right? Copper 2 plus could be gaining 2 electrons, copper 2 plus could be gaining 1 electron, and the values, the potentials are given over there. And similarly, I would have to look for equations for water as well, where water is gaining electrons. So there's an equation right close to it where you can see water gaining electrons. So look for the equation in the forward direction. right? All of these equations, I'm looking at them in the forward direction because at cathode, they're going to gain electrons. So you're going to write these three equations, and then you're going to decide. Then you're going to decide which one is going to gain electrons. The one that gains electrons or has the highest tendency to actually gain electrons, that's the one with the highest E naught. So you're going to look for the equation with the highest E naught. And that over here is going to come out to be the copper equation. That's the one with the highest E naught. Because remember, there is no H plus 1 and there is no OH minus 1 ions. Uh, it's different. O levels say it's different. Okay? It's different from O levels. The reason we chose O levels was because I mean, they weren't asking for the working, so you could have gotten the same answer uh, using the O levels method as well. The O levels method is not correct, but you get the same answers, so it doesn't really matter. Uh, but if you're supposed to show the working, then this is all that you have to do. You would have to show all this working, and you're going to show why are you selecting this equation, because it has the highest potential. Highest potential means it has the highest tendency to actually gain electrons. Up at दूसरी side, but what's happening on the other side? You have two options: water losing electrons or SO4 2 minus losing electrons. So over here, you're going to look for equations where they lose electrons. Now in the data booklet, they lose electrons in the backward direction. So open the data booklet again. You have water and SO4 2 minus. These are your two candidates. Uh, Try and see where they're losing electrons. So there's one over here. Okay, let me mark this. This is water losing electrons. Then there's another one right next door. There's another water equation where water is losing electrons. Again, think of it in the backward direction. So two equations for water losing electrons and SO4 2 minus losing electrons. It's probably this one in the backward direction. So you've got three equations now. So who's going to lose electrons? Electrons are lost by the lowest E naught. The more negative or lower the potential, the more tendency for the substance to actually lose electrons. So the lowest E naught is the one that you're going to select, and the lowest E naught, this one is 2.01, and in the top two, that's so this one is coming out to be the lowest E naught. So you're going to write this equation, but in the backward direction. Okay, it's going to be two water molecules losing electrons to form O2 and 4H plus 1. So if they were asking for the working, this is all that you should have done to answer the question. But since they weren't actually looking for any working, they were just looking for answers, and it was just a 1 mark question for each one of them. You're not going to waste your time. Just do your O levels thing and find the answer. ठीक है ये clear सारा मैडम सारा अभी is this clear?
Yes.
So next one is molten calcium iodide is electrolyzed in inert atmosphere with inert electrodes. Write equations for the reaction occurring at the electrodes. Uh, अब इसमें there is no confusion. There's no competition happening. There's just two electrodes. Two things. At cathode, it's going to be calcium 2 plus. You don't have any other thing, so it's going to gain electrons to form Ca. And at the anode, you have I minus 1, and it's going to lose electrons. It's a diatomic molecule, so it's going to lose 2 electrons to form I2. That's it. Uh, so that's simple. It's molten. That means there is no water. So you don't actually have to look for who's going to gain electrons and who's going to lose electrons. Now the electrolysis, identify the ion that is oxidized and that is reduced. I mean that's a basic question. Calcium 2 plus is reduced because it gains 2 electrons, and the other one, I minus 1, is the one that gets oxidized because it loses 2 electrons. अच्छा इसके बाद and this is about Faraday constant. So he's saying an oxide of iron dissolved in an inert solvent is electrolyzed for 2 hours with a current of 0.2 amperes. The time or current दिया हुआ है. So you can use Q is equal to I2 IT, and you can figure out the charge that is flowing through the circuit. 2 hours means 2 into how many minutes? That's 120, 60 minutes. And every minute has 60 seconds. So that's the time. And what's the current? That's zero point 0.8 amperes. Can you even do the math and tell me how many, kitna charge hai ye?
Is it 5,760?
How much? 5,000? 5,760.
Yes.
That's the charge that's flowing through the circuit. Now, once you have the charge, you can use Faraday constant. Faraday constant is that you know that 1 mole of electrons, they carry a charge of 96,500 coulombs. So you could use ratios. It's 5760 coulombs. How many electrons are being passed through the circuit? So how many moles? So cross multiply, and I think it's going to be 5760 divided by 96,500. What do you get? How many moles? कितने moles आ रहे हैं?
Is it 0.059? 9.
So you're getting 0.05, only up to 3 significant figures. How many moles do you have? Remember, he's using 3 significant figures everywhere.
0.0597?
So we found the moles of electrons that are actually passing through the circuit. And you're given the mass of iron as well. So the mass of iron is, now we can find the moles of iron as well. The moles of iron would be 1.11 grams divided by what's the MR. You have to be, because you have to write your show your working. You have to be very accurate with the values, because you're going to lose marks for this. Iron is it 55.8 or 55.9? Where's the periodic table? Just a second. So iron is 55.8. So how many moles is this?
Is it 0.0198? So 0.02?
0 point
0.01989.
so 0 point
So yes.
0.199, right?
Yes.
I think 199. So these are the moles of iron that you're getting. What's the ratio? Like, what's the ratio of iron and the number of electrons? The ratio is, like, you can probably see this. I mean, if you uh, it's 1:3, I think, right? There's Fe and 3 electrons, right? I mean, if you look at the ratio over here, that's 1:3. TK, is this clear? Sorry, is this clear? Adam,
Yes,
Abia,
sir.
is this? So that's 1:3. Now he said, did he tell us about what the original charge on Fe is? Uh, he's saying an oxide of iron is dissolved, uh, and the mass of iron produced. So Fe is the one that's getting produced, right? So that must be, Fe must be 3 plus, because it's gaining three. One Fe is gaining 3 electrons. So the oxidation number of Fe originally is going to be 3 plus. Okay, because remember he's saying that iron is the one that's getting produced. So one iron requires 3 electrons. The reason it requires 3 electrons to produce one iron is that Fe must be, it must be 3 plus. So we're done with this question as well. So ठीक है, let's start do the other 2 questions in the next class then. ठीक है.
Okay, Allah Hafiz.
Okay, take care. Allah Hafiz.